It's great to have Carl speak to us today about log-Noetherian functions.
Thank you very much. I'll talk about log-Noetherian functions, some relatively new concept, so I'm sure none of you have heard of it. And I want to start by motivating it with some slightly more classical thing called Noetherian functions, which is kind of due to Khovanskii and to Géron. And then I'll show what the log means and why one should switch to log-Noetherian from Noetherian. Okay, so my talk will have kind of two goals. One is just to tell you what it is, and they produce an effective o-minimal structure. So basically, whenever you do something for minimality, you can use them to effectivize it. So after the talk, you can just use these effective results, and you don't have to ever talk to me again. I'm kind of cutting down the branch on which I stand, as Bruno said in his talk. So I mean, it gives you effective versions of a lot of these like Pila-Wilkie point counting and that kind of thing. So that's one goal of the talk. And the other is to try to demystify it a little bit. So I think we're getting effective bounds, and I want to just explain a little bit about why you are able to get effective bounds, how you can actually...
Just real quick, is this in the sharp world, or is this a different direction?
This is not, I mean, conjecturally in the sharp, but so far I have bounds and they're not sharp. So yeah, but I'll say something about it. So okay, let me start with... I'll start with a very simple cell, which is just a unit disk to the n. So this is the context that kind of Khovanskii worked on, and later I'll generalize to a slightly different domain. So this is just the unit disk in my notation. And now let me say what a Noetherian function is. So if I have functions f1 up to fn from C to C, they are holomorphic functions. All functions will be holomorphic. I'll call it a Noetherian chain. If you have equations as follows: delta j of fi is pij of f1 up to fn. And here delta j is just derivative with respect to the j variables.
Capital Dij. Capital Dij there.
Capital P, sorry. These are just polynomials.
Okay.
Sorry. So, okay, that's just a way of saying that if we were looking at a ring R, which is C adjoined with these guys, then this is closed. Closed under these guys. Okay, so it's a finitely generated ring which is closed under all the partial derivatives. Okay, so I mean, this is what Khovanskii considered. To Géron considered the case that instead of finitely generated ring, you take a Noetherian ring. And you get kind of a similar theory. If you want things to be really effective, which is what Khovanskii was thinking about, then okay, you want some finite data. You know, if you're trying to do just some finiteness, you could think about the Noetherian ring here. Okay, so the idea is that when you have this, you can associate some kind of complexity parameter that measures how complicated everything is here. I don't want to get too, technical, but let's say that the format of this chain, it's going to be the sum of all the maximum norms of these fi's plus the sum of the degrees of the pij's and the, let's say, L2 norms of all these polynomials pi. I just mean the norms of all the coefficients as polynomials. Here I mean the actual maximum of all these functions, and here the degrees. So this measures of everything about this data that defines the functions. The thing to notice about this format, maybe if you're comparing to more classical things, I mean, Khovanskii.
These functions bounded on the whole disk?
Yeah, sorry. So they are all, they are homomorphic functions, and to have a format, they should be bounded. In fact, when I do the formal definition, they have to extend to a little bit bigger cell that I will mention later. But yeah, for now, let's say it's like this. They should be bounded. So one difference compared to the more classical case where we have good bounds. So the classical case is Pfaffian functions. So in Pfaffian functions, this system would have to be triangular. So the derivative of f1 will depend on your f1, derivative of f2 will depend on the first two. And then if you do it like that, you don't get this extra term here. You don't need this guy. Okay, so we get bounds that they are independent of these coefficients. And that's some difference. That is something that happens in the Pfaffian world, and it simply cannot happen in this Noetherian world. Okay, so a good example to think about is just sine and cosine. Okay, so if you do like, an example, if you do this C with sine of x and cosine of x, this is obviously a Noetherian chain, it's closed. And you know, in a big interval, it will have, so let me put even an m here. Let's say I did cosine of mx, sine of mx and cosine of mx. And okay, these will be bounded, but okay, the unit disk, they will have m over 2 pi zeros or something. So, I mean, you have to somehow account for these extra coefficients. So this will come in here. So without this data, it's clear that you cannot expect to get any effective bounds. With this data, maybe you can. Okay, so the conjecture by Khovanskii is that, so the number of, let's say, isolated, there's many ways to put it, but number of isolated solutions for system of Noetherian equations is bounded by some effective bound in the parameters. Okay, so I should say Noetherian equations means any element from a ring like this. Okay, so this is like the function that generates the Noetherian ring, and any element of this ring I call the Noetherian function. So now you impose a bunch of Noetherian equations, and you would like to say that you can bound everything effectively in terms of this data. I mean, Khovanskii wasn't very precise about what effective means here. A bit later, I mean, there was a slightly different conjecture by Gabrielov and Khovanskii, where they wanted this to mean primitive recursive. So, which is like natural to expect. But I mean, I don't want to get
Isolated means in the usual topology.
Yeah.
You see isolate.
I mean, yeah, it's just so that you can, if I just said the number of solutions, well, maybe there's infinitely many. You could say the number of connected components, or you could formulate this differently. But I mean, basically, you want to be able to say that once I defined functions using differential equations, then I can control the complexity. And this is the conjecture. Actually, Khovanskii made this conjecture, I think, before he studied Pfaffian functions. And because there was no progress there, he decided, he kind of found out that if this is triangular, he could get much better things. And this is kind of historically how it developed. And maybe the main reason for this conjecture was actually period integrals. So it's quite related to our problem now. I mean, the problem they were thinking about is just zeros of abelian integrals. This comes up in Hilbert's 16th problem when you're doing perturbations for Miltonian systems. So he was thinking about that case, and he was coming up with a class which would let you control the kind of geometry of things connected to period integrals. I should say that this is not quite enough for controlling period integrals, because these equations are kind of non-singular equations. Okay, so this would allow you to control solutions of systems of differential equations away from the singular locus. It wouldn't quite cover period integrals, for instance. If you want to encode them as solutions of equations using Gauss-Manning connections, it will work away from the singularities. So that's one reason to try to generalize, but it's not the main reason why I want to generalize. Okay, so now, yeah.
Is there any intuition why this number should be finite? So like this number of connected components, like just.
Why? I mean, it's kind of finite because everything is compact, right? They are defined on this compact domain, and they're all analytic there. So it follows from, let's say, general o-minimality. Kind of just, if you take any collection of analytic functions and you impose a set of equations, you will have a finite bound, right? It's an o-minimal structure. There will be a finite number of isolated solutions. But that's a very general thing about just analytic functions on compact domains. like a kind of the uniqueness principle for, holomorphic function or a compact domain can have infinitely many zeros. It's kind of a multi-variable extension of this. But why there should be kind of, some explicit bound that, there's no intuition.
Maybe bound is not enough for what you're saying now. Maybe you really need like over-convergent or something, even if you just assume holomorphic on the
No, it's holomorphic on the closure. So it's really, these are holomorphic functions on the closure.
But then it depends on.
Yeah, kind of by definition,
But then
by my definition. Yeah, but sorry, maybe I'm simplifying my notation a bit too much. In fact, they should be, I should define a little bit bigger cell, which I will do, and they should extend to a slightly bigger domain, and then it will be clear. But yeah, when I write holomorphic on C bar, it's actually holomorphic on a slightly bigger disk.
So one more question. Is it clear from like general principles like what you're saying now that there's some function of the format which bounds the number of Affiliation solutions?
I think it's clear probably from
Just some sort of Noetherian argument or something?
I think it should be clear from maybe o-minimality, although it's not very easy because you're varying over all of the
Seems tricky, right?
different
Sign of MX example shows you can't be just o-minimality.
I think, it's a question of can you show that the dependence of these analytic equations on the parameters that, you're kind of changing the differential equation and you're asking, is this dependence o-minimal?
Right.
If you're in a compact domain, it's bounded, probably it is o-minimal, but let's say if you did it in the Pfaffian case, it wouldn't be obvious. When you get some uniform bounds, when you take different Pfaffian systems, but dependence on the parameters in the Pfaffian system is not definable, so I'm not quite sure yet.
But Gal, what about this? I think we had a conversation about this at one point. Like you have this counterexample in Rn, where something rose sort of non-computably fast or polynomially fast. You should be able to write down some series like this that.
Yeah, so there should only be like I'm only saying there should be like a uniform bound for every fixed degree of the equations, but there is no computable bound in general. If you're just taking analytic functions. I think I understand what you mean, but let's discuss it. Okay, so let me say a bit now about what is this Log-Noetherian. So now I'll change it to the LN.
Conjectures and so.
The conjecture will follow from a theorem for Log-Noetherian that I will now make, which is solved. So it's actually the conjecture is solved. So now I'll replace C, this my domain. Now it will be a product of maybe potentially punctured disks and annuli. Okay, in fact, I need something slightly more complicated than this, but let me leave it with this annuli for now. And what I'll do is I'll change these derivatives that I take. So I'm going to take delta j to be just the usual d by dxj if we're dealing with a disk. If the coordinate is a disk, but I'll take delta j to be xj to dxj if we're dealing with a punctured disk or an annulus. Okay, so and the rest of the definition I'll keep the same. So I'm taking now functions, they will be defined on, let's say, a product of punctured disks. But now the derivation is not d by dxj, it's xj d by dxj, so it's kind of with a logarithmic singularity. So that's why I call it like Log-Noetherian. And this turns out to be very kind of important for the inductive proof. Okay, so in fact, I would say that the reason that we couldn't make progress on this conjecture of Khovanskii was that it was kind of the wrong generality in which to try to approach this problem. Okay, so let's say what the theorems are. So the theorem is this conjecture of Khovanskii holds for Ln functions. Okay, so every Noetherian function is an Ln function. Okay, so it's easier to be closed under this than to be closed under this. Okay, so this in particular implies this Khovanskii conjecture. And let me give a more general form of this theorem. So I'll denote by RLN this structure generated by all Ln functions.
Probably you should give us a function which is log and not the other.
I will give you, it's not so easy to give an example, but
No, it's not something we've all seen.
yeah, it was quite, I mean, for me, it took, even after I finished developing this theory, I did not have an example. I mean, I could just prove things in this Log-Noetherian case, and I couldn't prove it in the theorem, but later I found a nice example that really shows why you have to best to Ln, and yeah, I will show it. Okay, so Ln is this structure that's generated by all the Ln functions. It's o-minimal because it's a reduct of Rn. And the theorem is that this structure is effective. So Rln and Rlnx are effective. Again, I don't want to be too formal about what this means, but what I mean is if you write now any formula involving Ln functions and exponentiation, then the finiteness statement of o-minimality you can now make effective. There's some explicit function, in fact, even primitive recursive of the formats of all the functions that bounds the number of solutions. And this kind of follows this and this. This, of course, implies this. And you know, the conjecture for equations was like the main difficulty. So the tools that allow you to count solutions for equations, they actually already allow you to build an o-minimal structure. But the reason to like this is that this actually puts all the period integrals. So period integrals and therefore also period maps, at least for okay, all period maps in fact are in the structure, but okay, if it's a period map of a geometric VHS, it will follow from the fact that period integrals are definable. They're all in this Rlnx. Let me just briefly explain why. So if you write a period integral or any section Gauss-Manning type connection, you can write it like a sum of some aj of t times the lambda j times logs of t to the kj. Right, so this is a finite sum, so j goes from 1 to d. And now these guys are themselves going to be solutions of regular singular equations. But these guys are holomorphic. So these are actually Ln functions. Okay, they are solutions of linear equations. The fact that they become Ln in this form, that's exactly the Lin's definition of a regular singular connection. And now these guys are not Ln because Ln functions need to be holomorphic. Okay, it was the first question. I'm allowing singular equations, but I still want holomorphic functions. So these are not in Ln, but they are essentially in Rx. I mean, on the real line, they are really in Rx. In fact, you should add also restricted elementary function. You need like sine and cosine to get them, but never mind. But so these are essentially in Rx. These are Ln, so everything is definable in Rlnx. But the way that you get bounds for these kind of things, it involves two very different approaches. So in Ln, you are using some kind of algebraic holomorphic machinery. And then the way we get this extra exp is exactly Khovanskii's classical way. So we are just kind of relativizing this construction of Khovanskii. He does it over polynomials, but he doesn't really need polynomials. He's basically saying, with polynomials, I have Bezout, and now I can add exp and I'll still have bounds. So now with Ln, you have some kind of Bezout, and you can add exp and still get bounds. Okay, so this is the idea of the construction. Okay, so I want to kind of try to demystify this statement about Ln and explain how to think about these Ln functions and how the proof goes in very vague terms. So I will need to talk a little bit about these extensions of these cells. So as you already noted it, I need the functions to extend a little bit. So I'm going to denote by, if I have a disk of radius r, I'll denote its 1/2 extension like this. I'll put a half here. That's going to be D2 now.
Sorry, is the example, is T one variable?
I mean, I wrote it easily for one variable, but you can do it for any number of variables, like any. First, you pass to a normal crossing divisor, and then if T is multivariable, you can still expand like this. You should have some matrix exponent here, but it all works out.
Actually, the Khovanskii.
Like Valchenko. Well, I mean, Valchenko and Khovanskii basically they got
They reduced it.
Valchenko Khovanskii basically Valchenko, but using Khovanskii basically showed that without the effectivity you have this theorem. So before there were all minimal structures, and before that he showed that if you take any number of equations involving period integrals, even in several variables, then you have a Bezout theorem. Not effective, but you have like some uniform finiteness. And the way he did it was exactly like this in some, I mean, before this language of o-minimality existed, he wrote it like this, and then he said, okay, these are analytic functions, and now I can kind of do Khovanskii's reduction over the analytic functions, and I'll get some uniform bounds, but not effective, because I don't have effective bounds with the analytic. So here you are kind of just getting the analytic part to be effective, and the rest is Khovanskii. Okay, so I have this notion of extension. If I have an annulus with 2 radii, will be okay. So this is a disk of radius r, and this is an annulus with 2 radii. So when I put this little half here, I mean that the outer radius I'm increasing by 2, and the inner radius I'm contracting by 2. Okay, so now let me state the theorem that I am actually proving to prove all of this, and it's in some sense more algebraic. So the theorem, which we call the cellular parametrization theorem, is as follows. So suppose you have a collection of these ln functions that are defined on a slightly bigger, on the C1/2 into C. So I have ln functions that are defined on a slightly bigger disk. Or okay, now C is a product of this scenario, and each of them I increase a little bit. So they are all ln functions. Then the theorem states that there exists a cover. So it's a collection of maps from cells into my cell. So I can find a collection of cells that cover my cells such that the 2 things happen. The union of the images of these CJs contains my original cell, and the pullback Fj star of Fk is either identically 0 or non-vanishing. So let me tell you what it means in a picture, because it's a bit hard to math. So basically what I'm doing is I'm taking a cell. So I have a cell C, and inside I have a bunch of the zeros of a bunch of functions. I have like F1, F2. And what I'm saying is that you can now find cells that will cover this whole thing. So I can find a bunch of cells. One of them maybe will map into this region. I'll have one cell that maps into this region between the yellow line. So this will be the image of one cell, C1. I'll have another cell, C2, that maps into the 0 locus of this. Like this thing will be the image of a cell, C2. I don't know, the yellow one, this guy will be the image of a cell C3. And so on. Okay, we get a bunch of cells, and each of them, they lie either completely in the 0 locus of F or outside the 0 locus of F. So we are covering the whole domain by images of cells, and kind of the intuition is to is to think about this as resolution of singularities, a form of resolution of singularity. So I'm thinking about the idea is that this CPT is like a local resolution of singularity, and I'll explain why.
Are you claiming there's like a bounded number of these, or does it exist?
Yeah, sorry. So I'm claiming that, yeah, that this is effective.
When you say the pullback is non-vanishing, are you like restricting to CJ in CJ 1/2, or no, really the pullback to CJ 1/2?
It's like non-vanishing. I mean, it's nowhere vanishing. Maybe I should. And yeah, even on CJ, even on the 1/2. Yeah, even on the big one. Yeah, but I should have probably just to be clear said nowhere vanishing. So it's either 0 or it's nowhere vanishing. And yeah, of course, the main point is it is effective, right? So this result, if you just do it analytic, not effective, this was in my paper with Dimitri, called complex cells. And we also made it effective and even sharp in the algebraic case. Okay, so if these are all algebraic, then we can show that there exists such a cover, and even it's a polynomial number in the degree of cells. And okay, and this we used. So improve the Gromov lemma, sharper, and I mean, so this is kind of based on some development that I had with Dimitri before. But yeah, the main point here is that this is effective now.
Yeah.
And kind of this language allows you to do some induction. Okay, so I mean, actually, I prove it like this, and the fact that you get this allows you to do some induction on dimension that you couldn't do if you just try to prove Bezout theorem separately.
So here by effective, you mean that the Fermat of this, that the number of FJs and their complexity is bound?
Exactly. Yeah. So there's some bound on how many, and there's a bound on the complexity of each of them separately. Okay. The actual theorem is more detailed. It's important that here I don't just take 1/2. I can get a bigger extension because that helps in the induction, and these maps have a very special form that forces the image to be actually a cell when you restrict to the real part, a cell in the real sense. So there's more details to this theorem, but this is kind of the rough idea. But what I want to kind of explain is why you should think of these as resolution of singularities, or at least as passing to a monomial form. So it's a resolution of singularities in the sense that you can take any collection of divisors and put them in the normal crossings. Okay, so our cells are like, I said, let's say a product of punctured disks. So it looks like a normal, like the complement of a normal crossing divisor. And I'm claiming that each of the functions is going to become a monomial times a unit. Okay, so like this, when you pull back by Fj, you get a new chart where each of your function became a monomial times a unit. Its zeros are going to be only in this, along the vanishing of some of the coordinates, the ones where you have punctured disk. So the way to make this explicit is the following theorem. I call monomialization lemma. So the theorem says that if you have a function f, again from some extension of a cell, and now it's a non-vanishing function. So recall, I was saying that each of my functions, after I pull them back, they're either identically 0 or they're non-vanishing. Okay, so if they're non-vanishing, okay, and it's ln, so let this guy be ln. Then I claim that you can always write f in the form some constant, depending on f, times x to some monomial, x to some power, times a unit. And this unit, so where u is ln, you can take out a monomial and you'll be left with an ln function. And I claim that you have effective bounds. So for instance, this monomial alpha f is bounded effectively by the format of the functions. And the unit, the format of the unit is bounded. And also, if you look at the unit, it's always bounded between 1 and 1 over some effective number. Okay, so it's really, you have to think, what does it mean for me to prove monomialization in effective form? So monomialization means that I'm a monomial times a unit. And what does it mean to have a unit? It means something that's bounded away from zero. But if you really want to be able to now use this effectively, then you have to know not just that it's bounded away from zero, you have to know an effective bound. In fact, this effective bound, it depends on the extension. So if you make this extension bigger, you can even make this unit newly constant, okay, in some controllable way. So this is kind of the intuition why I think of this CPT as kind of an effective form of resolution of singularities. And in fact, even in the classical case, even in the algebraic case, if you want to make resolution of singularities effective, you have to allow these annuli. I mean, it simply wouldn't work. The resolution of singularities, if you're working just with punctured this, it works for a fixed, like algebraic variety, but it does not work uniformly in families. It's a known phenomenon. When you're working in families, you can put the whole family into like a resolved form with the map, like the map itself becomes monomial, but you cannot uniformly make each fiber monomial. So this is why this extra complication comes in here, where we have to allow annuli here and so on. But I don't want to go deeply into that. I want to maybe justify a little bit more why I think of this as resolution of singularities. I'll just show you what Dimitri and I kind of noticed when we were developing this just for the analytic case. And in fact, from hyperbolic geometry, that really convinced us that this is a good analog of resolution of singularities.
Maybe I missed it, but why CPT?
It's a cellular parametrization theorem.
Gotcha.
Yeah, I did not write it.
The classical case with Fi being polynomials, this would give you not the classical resolution of singularities because you wouldn't get Fi, small Fi as polynomials.
So if you are doing the classical case with polynomials, you can get these Fi's to be algebraic.
But your method would not give algebraic Fi, it would give something else. Like if you just run your method through in the classical case, you would not get like a classical resolution.
I mean, if I use the theorem for Ln functions, I'm not quite sure. But we do have a theorem with Dimitri, which is older, which shows that if you start with algebraic, you can make everything algebraic, and then even there's a very good bound. And so this is kind of the first case we considered, and now I'm trying to use the same machinery for this Ln case. So I want to explain, I mean, one of the reasons why we like, okay, how does resolution of singularities work? Let's say you're doing very simple resolution of singularities, a local resolution of singularities. So not this global Hironaka thing, but just local resolution of singularities. It's a fairly simple proof, and it's based on a very nice, reduction, which I guess is due to Hironaka. So the reduction says that if you can monomialization, that implies that you can also principalize ideas. Okay, so once I know how to take a collection of functions and turn them into normal crossing dividers, I can also take any ideal and make it principal. And that's, I think it's maybe due to Hironaka. It's a very simple thing, but Hironaka used it. And the idea is as follows. If you have, suppose that you have a collection of functions that they generate an ideal and you want to principalize this ideal. So suppose that I take every Fi and I take every difference, Fi minus Fj. So, and suppose that I monomialize, or suppose I pass to a chart where each are monomial times a unit. Then this implies that either Fi divides Fj or Fj divides Fi. If you just think about the zero locus, where these differences vanish, if one did not divide the other, then the zero locus would not be monomial itself, would not vanish only on the coordinate hyperplanes. Just a very simple exercise, you can do it. And then this implies that this ideal F1 up to Fn, no, is principal. Okay, because you know that for every two, one divides the other. So eventually the ideal generated by all of them is just generated by the one that divides everyone else. So now I want to make a claim like this, but more kind of effective, something that you can. So this idea, it works by compactness. I mean, if you think about like near zero, if you think about the zero locus of this difference, it can't be monomial if they didn't divide each other. But it's not something that you can effectivize.
So, sorry, Gail, I'm going to slow you down. Just what you're sketching here is the proof that if you have a local singularity, like an isolated singularity, you can resolve it.
I mean, I'm not really sketching the proof. I'm just saying one of the main ideas when you try to resolve singularities is, I mean, you are working in a certain dimension, then you want to go to one dimension lower and you want to make some ideal principle. And what Hironaka uses is that if you know how to make functions into normal crossings, then you can make an ideal principle. So this allows you to do this inductive step. So, I mean, it's a bit hard my proof doesn't exactly follow these.
This claim here at the end with Fi and Fj's, are they like germs at a point or are they global functions?
I mean, when Hironaka does it, it's germs at a point.
Okay, but for you it's going to be...
But for me, I mean, I don't want to work with germs because I want to get effective bounds. So I need like something that looks like this by analogy, but it's not really the same statement. So that maybe when I show the statement, hopefully it will be somewhat clear what I mean. So the lemma that I want is something like this. So suppose that you have a function. Now it's not even a ln, just about holomorphic function. You have a function that's defined on one of these cells with a half extension into c minus 0, 1. And I claim that it automatically follows that f is either less than 10 or...
Sorry, that's an annulus, right?
Now it could be an annulus or a disk, or also even a product of several of them. So I'm claiming that either f is uniformly on the cell, not with the extension. So you are defined and you don't take the value 0, 1 on the bigger cell, then on the smaller cell you are bounded automatically. Why do I say that this is the same statement? Take two of these functions and look at the ratio. Okay, so if I have two functions such that, for me, being monomial means the function does not vanish, right? As I said, I'm trying to arrange that the pullback does not vanish. So now I'll have two functions where neither of them vanish, but also the difference does not vanish. So it means that the ratio is not taking the value 0, infinity, and 1. Okay, and then I'm saying that the ratio is uniformly bounded either by Carol. So it means one of them controls the other uniformly with an explicit constant. And again, this tan actually depends on this 1/2, and you can make it as nice as you like. Okay, so let me kind of show the proof. This was kind of the theorem that surprised Dimitri and I, and that kind of gave us this idea that this should be something like resolution of singularity. Okay, so first of all, for a disk, I claim that this is very simple. So for C is a disk, I claim that this just follows by contraction principle for holomorphic maps. Okay, because then the diameter inside C minus 0, 1 of this set f of C is going to be less than or equal to the diameter inside this d1/2 of D. Okay, and this is just some constant, okay, pi or something. So we have the disk inside the bigger disk, the map just contracts. So now you're landing inside C minus 0, 1, but you have a small diameter. So definitely you cannot go from, I mean, these 2 points are kind of far from each other in the hyperbolic metric. So that's not what's surprising about this statement. The surprising thing is that you can make the same statement even when C is an annulus. Okay, so let me remind you what the annulus looks like in the hyperbolic metric.
What diameter of D1/2 inside D, I assume? I'm
Say again?
struggling to parse. Is that are D1 half and D flipped there, or am I confused?
So this is the ambient space,
Yeah.
right? And yeah, so I'm saying the D inside is the bigger. So if
Okay.
okay, yes, but maybe there's 50% chance I flipped something here. Okay, so let me show you what happens for an annulus. Let's say you take an annulus between epsilon and 1. So I want to draw the annulus. So like this bigger annulus, that's a 1/2. Okay, this kind of is the boundary, goes off to infinity. This here is A, the original A. Now, what are the distances? I'm claiming that this one is constant. You can find this one is constant. This one is roughly log epsilon.
Meaning the hyperbolic.
Hmm?
What metric? The hyperbolic?
This is, yeah, I'm drawing the hyperbolic metric of
Yeah,
1/2, and I'm drawing A inside.
I'm just asking what metric.
Yeah, it's all the hyperbolic metric. So the important things to note is that this is like a tube that's getting longer, but the sides are remaining constant. In fact, this one is also getting pinched. So this one is tending to 0, but okay, that's somehow useful, but
This is algebraic in some sense.
but not for the proof now.
We live with this when we deform, Riemannian metrics. So
Yeah. So I mean, this is really the formation.
we're color.
This whole theory is about the formation of the holomorphic structure. That's why it comes up. Okay, so now you should be surprised, because if I repeat the same proof as here, I'm going to take this tube and I'm going to map it to C minus 0,1, but okay, it could be very long. I mean, it could have length log epsilon. So the idea is, okay, so suppose that the theorem is false. So suppose that F is sometimes, so let me draw C minus 0,1, so I'll have, this is 0, this is infinity, this is 1. Infinity. And suppose that my image somehow lands very close to here, but also very close to here. So there's a point where it's less than 1/10. So in fact, I mean, okay, let me draw. If my annulus looks like this, then just by the open mapping theorem, it's clear that this circle should go somewhere here. And this circle should go somewhere here, maybe even around. Okay, because I mean, the point where I'm very close to the point where I'm smallest has to occur on one of the circles, right? Maybe this circle goes here and this circle goes here. Right, the boundary of the image goes to the boundary. You have maximum and minimum principle. So one of these guys should go close to 0 and one should go close to infinity. But this loop is quite short. And the point is that this loop is not long enough to wrap around 1. Okay, you might wrap around 0, but not around 1. And this one can wrap around infinity, maybe. But again, not about 1. So, but they are homotopic. Okay, so this should be homotopic to this. So we have the homotopic class of this in the image should be only generated by 0. Homotopic class of this should be only generated by infinity. So this implies that actually this, what did I denote it? F star of pi 1 of C is trivial. Okay, inside pi 1 of this C minus 0,1. Okay? Now, once you know that it's trivial, you can essentially go back to the previous case. Okay, so we can say that, yeah, so we can lift it, right? So let's go from C, we have this map that goes to, we have the map F that goes to C minus 0,1, but actually it can be lifted to a map, this is F, it can be lifted to F tilde that now goes into the universal cover, the upper half space, like this. Okay, now let's look at the boundary of the image of this F tilde on C, this is going to be contained in the, the image of the boundary. That's just the open mapping theorem. And this guy has bounded length again. And I'm saying that the image of this, the boundary of the image is the image of the boundary, and we said that this boundary has bounded length in the hyperbolic domain. So this, the image of the boundary is going to have bounded length by Schwarz. And that implies, because of the isoperimetric inequality, so that F tilde of C has bounded diameter. Okay, once you're in the F space, you can bound the diameter by the length of the boundary. This is not true in C minus 0, 1. That's why we had to go to it. So this is how it's proved, and this is kind of why hyperbolic geometry really enters into this theory a lot. So if you're trying to make it more effective, you should really not just get bounded length. You want to control quantitatively how this length varies, and you can see, you should just compute these lengths in the hyperbolic metric, and if you arrange to have a bigger extension instead of A1/2, you can make this smaller, and this is how we get like a sharper bounds. Okay, but now I want to go back and explain why we have to go to ln. Peter's question. So you can see it already from this monomialization lemma that I mentioned. Okay, so the monomialization lemma, I said that when you have a function, you can always write it like monomial times a unit, and the unit is ln again. So what happens with if you try to do it with Noetherian function? Why the L in ln? So let's consider the example sine. So sine, the sine function, let's say just on the disk. So this is a Noetherian function. Okay, you don't use L for it. It has a very simple Noetherian chain. But I claim that the unit is not going to be Noetherian. Okay, and this is what I always thought and could never prove. Okay, so if we write it like a monomial times a unit, that would be writing sine of x is equal, well, it's x times sine of x over x, right? And this would be kind of our unit. And this would be u. So the monomial is x and the unit is u. The question is this function Noetherian? But that's not so easy to check. I mean, seems that if you take a derivative of sine x over x, you'll get something over x squared. And then you derive again, you get over x cubed. So maybe you cannot write it like a polynomial in the previous ones. But on the other hand, maybe sine, when you take the fourth derivative, it's going to be the square of the second derivative or something. It's not so easy to rule out that you have some relation like that. Okay, so, but I claim that you don't have a relation like that. Let me show you why. Roughly show you why. So the idea is that if u were Noetherian, then I claim the following. Look at the sequence of all derivatives. Un at 0 for every n. I'm claiming that this should have finitely many primes in the denominator. So let me roughly explain why that is true. I mean, okay, if it was Noetherian, then it should be that when you take a few derivatives, after a certain derivative, everything becomes polynomial in the previous derivative. You might complain that, well, maybe these polynomials contain some transcendental numbers or something, but I mean, you can show that this does not happen. So in fact, if it were Noetherian, it's quite easy to show that it would have to be Noetherian with algebraic coefficients. And then if you take all the p-adic places where these coefficients are positive, you can't get any new p-adic places when you start taking derivatives. Right? But it's simply not true. I mean, if you check you compute, you'll see that u n 0 in this case equals to -1 to the n divided by I guess 2n plus 1. So you do get infinitely many primes, so it can't be Pfaffian. And so this is one of the reasons why I think that this theory probably makes sense and is interesting over the p-adic numbers. Okay, so I'm developing everything in the Archimedean place, but actually everything makes sense for all the p-adic places. Maybe I'll get to show a little bit more of the construction and what makes sense for the p-adic places, but there's actually interesting information here to be seen. Like you can detect if a function is Noetherian or not by looking at how the derivatives behave in the p-adic places. Okay, so in the last 10 minutes or so, I want to try to demystify a little bit more. So far I talked about, we try to do resolution of singularities and we get some uniform constants, but it's still not clear how things should depend eventually on the differential equation. When eventually somehow we start with a differential equation, we're going to get some numbers. And I want to just explain why this happens. So the main idea is that when we have Noetherian functions, we can get a good control on the variation of argument. And using variation of argument, we'll control various things. Like let's say I want to control this this exponent x to the alpha f. It's clearly going to be controlled by variation of argument. Or you want to count zeros of a function, you need control on the variation of argument. So the theorem. Oh, okay. So I'm going to explain about bounding variation of argument. And by the way, this is also the reason why everything I do is restricted to holomorphic functions. I want to be able to say that I have a holomorphic function, and for instance, if I control the variation of argument around the boundary, then I have a bound for the number of zeros. If you allowed something like log, then it wouldn't work. That's why I have to separately put in the logs later using Khovanskii's approach. Okay, so how do we bound variation of argument? There's a very nice theorem, essentially due to de la Vallée-Poussin. So de la Vallée-Poussin, which states the following. Suppose that I have a function f, let's say on the unit interval into C, and suppose that it satisfies a linear differential equation. Fn plus something. It goes from -1 to 0, Cj of x, j equals 0. So I have a linear differential equation, but moreover, it's without a free term. So I have a linear differential equation, and I want all the coefficients to be bounded. So let's say where the Cj's are analytic. I don't think you even need analytic, but in something, for me, there will be analytic, and the Cj in the infinity norm is less than or equal to some constant n. Then I claim you can bound the variation of argument of f according to this number. Okay, so
Why was he deriving that?
what?
What was he using it for?
Okay, let me be a bit more precise. So what de la Vallée-Poussin proved is that you had a real function and you are controlling the number of zeros. And why exactly was he doing this? I'm not sure, Dimitri, do you know? Why de la Vallée-Poussin wanted this theorem? It's super useful. How could you not want it? But
I guess because I wonder if
It's nice.
he's famous for proving the prime number theorem.
yeah, well, I don't know if you use it for that. But yeah, I'm not sure actually. I've never read I even asked Dimitri yesterday if he knows who exactly. So this was for zeros. Then I stated variation of argument. It's very similar. You can actually get the result for variation of argument from the results of zero. So I'm attributing it to de la Vallée-Poussin, but it's not exactly what he proved. But anyway, let me write the conclusion, then the variation of argument, okay, along this interval 0, 1 of f is bounded by some variance. So there's some c times the order n, and this c is some absolute constant. Absolute. Okay, so if we have a linear differential equation, we can control the variation of argument. The idea is to try to use this, but okay, you cannot immediately do it because the Noetherian equations are not linear. They're just arbitrary equations.
N plus.
What?
Right, M plus 1.
M plus 1.
Oh. Go for 0.
Yeah, it's a real logician seminar here. It has to be logically accurate.
True.
M plus 1.
M or M.
M or N?
M.
M.
For M equals 0.
Oh, I mean, he's worried, yeah, worried about M equals 0. Okay, so now I want to go from Noetherian functions to this, and there's actually a very simple way to do it, modulo the theorem by. Okay, so now what is the proposition? And this proposition is following. And Novikov and Khovanskii. So, okay, I'll state it like this. I said it in this ln language. So suppose that you have an ln function on a cell of dimension 1. If ln, again, you can prove it for any dimension, but let me just be simple. So you have an ln function of one variable. Okay, so let's say I have a disk and I have a function that's satisfying some general nonlinear equation on this disk, on a punctured disk. Then I'm claiming that the variation of argument along gamma, let me tell you what is gamma, of f is less than or equal to some effective thing depending only on the format, where this gamma is a component of the boundary. Okay, so I can, if it's a disk, take the outer disk, and I'm claiming you can do the variation of argument on this outer disk, and you can write a bound for it. It will essentially follow from this theorem. So the question is, how do we get a linear equation? Let me explain that to you as the last part. So the idea is very simple. We'll use Noetherianity. These are Noetherian functions. So recall that my f is just an element of this ring R, which is C adjoined with F1 up to Fn, like my original Noetherian ring. Now I'm going to define a chain of ideals. So I'm going to define a chain of ideals Ik, like an increasing chain in R, and I'll define them by Ik is equal to F delta F delta to the k. Yeah. So it's an increasing chain of ideas. It has to stabilize in this ring. When it stabilizes, what it means is that we got an equation delta kf is equal to some sum Tj times delta j as j goes from k minus 1 to 0, and these guys are just elements of R. Okay, so this is an equation, a linear equation of the type I mentioned with respect to this derivation. Now, the little bit important thing to note is that with respect to this derivation, the boundary components have like a constant length. Okay, so if we are dealing with a disk, then this derivation is just d by dz, and the boundary has a constant length. But if we're dealing with an annulus, and the derivation is x d by dx, then again, the length of the two circles is going to be constant. Okay, so if you apply that, I stated the Lavalette-Poisson straight line, and here, if you pass to the log scale, this will be straight lines, but never mind. Essentially, because this length is bounded, the Lavalette-Poisson applied to this will give you what you want. The only problem is I use Noetherianity, which is the biggest mortal enemy of effectivity. So, I mean, if you just define a chain of ideals and say, well, it stabilizes and then something happens, this is the most non-effective thing you can do. I mean, it's right. I could encode any problem by like saying that some chain of ideas stabilizes, but there's something special about this chain of ideas, which is that what I really want is that the first time that it stabilizes, right? Once it stabilizes, it's stable forever because I'm just adding derivatives. And in fact, that is an effective problem. If you have a chain of ideas, and you're just looking for the first stabilization, this is always effectively solvable. This is by some like very general like arguments. Who did the Seidenberg? Seidenberg? But here you can do much better. Here, because these are derivatives, then you can actually use effective commutative algebra. And actually, what is the crucial point that Dimitri and Sergei did is that using commutative algebra tools, basically Grobner basis type stuff, shows you that this index of stabilization, so the k is such that ik is equal to ik plus 1 is effectively bounded. I mean, they have like a much nicer bound. In fact, it's even polynomial in the degrees. It's quite bad in the dimension, but you get something much better than Seidenberg because this is just a sequence of derivatives. And moreover, once you have a bound for that, you can even get a bound for the degrees of these guys. Again, it's just Grobner basis computation. These are all polynomials of bounded degrees. If you know it's stabilized, then you can get a bound for these, and you can get a bound for their norms. Like everything about this equation can actually be computed effectively. That means that you can get an effective bound on the variation of argument, and then you can bound the monomial, and so on. Now, I should say that, I mean, this is what they did, and what they did actually solved the problem in dimension 1. So, I mean, as you see, it's quite easy to get from their result to a proof of this solution of Khovanskii's conjecture for dimension 1. So, the real difficulty was that we don't know how to do this in several variables. So this is what I've always been stuck on. It's not clear how you can define a chain of ideals that when it stabilizes, it will bound the number of solutions for a system. That's what I could never do. And the way that this is actually overcome in my approach is that if you have two equations, you look at the first one, you somehow desingularize it. So it becomes like a smooth curve. And then you restrict the second function to the first curve, and it's already a one variable thing. So you can, there's kind of an induction that uses the fact that you can resolve singularities to then pass down in the dimension. And eventually you always go down to this result. Okay, I'm out of time. I'll stop here.
Questions?
Where's your paper?
Okay.
Where? How is?
I don't even
I
remember.
remember.
It's at year and some, year and a half.
Have you actually put parameters in?
What do you mean put
It's
parameters?
effective and you put numbers depending on all data.
I did not work out in fact, the reason why it's on the archive and I haven't even submitted anywhere is that I had the hope of, I mean, my conjecture is that this RLN should be even sharp.
Yeah.
And then you should
Sharp is some dependence.
sharp, it means polynomial dependence on the degrees. And I mean, there's a problem with this step where it's not really sharp, and there's a problem in other steps. And I had some ideas for how to maybe approach it, but I mean, so far I cannot say anything, and I didn't bother to write down explicit dependence because I'm sure it's a lot of work to get this dependence, but it's not the right thing. It should really be sharp. So I'm not motivated to spend my time on computing the annoying bounds. Yeah.
I'm curious here for the step that you give us this nice example of sin x over x, which is Log-Noetherian but not Noetherian.
Yeah.
to what extent do you have, and this is a very naive question, like if you were talking about vector bundles, like with flat connections versus log flat connections, you could very easily give examples and lots of algebraic structure there. In this setup, do you get any mileage out of thinking of these things as like, I don't know, vector fields on varieties? Do you have any sort of classification theorem that's at all, is that perspective at all helpful? Because you're doing algebra, you're resolving singularities in some way. I just wonder.
Yeah, so when I think actually about the Noetherian one, not the Log-Noetherian, it's quite helpful to think about it as a foliation.
Yeah.
So I have other sharper results where I get actually, for instance, this result that was used in proving Galois lower bounds, that is more comfortable to write in foliation language. There's no difference, as you say. I mean, these are really just collection of vector fields, you can say, that are commuting. But it is quite helpful to think in the total space in terms of foliation and to characterize the locus of unlikely intersection between the whole foliation and the variety. Here I have somehow, I haven't done it. I don't know if you get mileage. I think if you're trying to do, let's say, all places at once, which I think should be interesting, then maybe this would become kind of important, but I don't know exactly how to do that. But I mean, it's quite possible that I'm just not an algebraic geometer. So maybe there is mileage to be made, but I simply am not the one to correctly make it.
Other questions, comments?
Can you say a word about why the p-adic stuff comes in? That seems quite important in this particular place. Do you think that's a feature of the theory?
So I mean, on the one hand, I noticed it comes in when I was just trying to show why this function is not Noetherian, and I was stuck. I couldn't find any. I wasn't thinking p-adically. I was just thinking, in the Archimedean place, I have this function on R, and I couldn't figure out any way to see that it's not Noetherian. But from the p-adics, you see it kind of instantly. Okay, so, and then on the other hand, another thing is that this, like my main tool, that everything reduces to this eventually. I put a C here for no reason. I should have put a Z here, right? I mean, Z, F1 up to Fn is also Noetherian. That's a stronger statement. The equation that you get here is, you could actually write it with integer coefficient. It means you got an equation that holds on all places at once. So you have something like a variation of argument bound that holds uniformly for all places. So it just feels to me like a crime to, you have Noetherianity over Z, and then for no reason you localize to characteristic 0 and you lose a lot of useful information. But what exactly is the theorem that would capture all these other places is a bit hard to. The people in model theory do this. I mean, there's in motivic integration, people often, they have these preparation theorems, which are very related to the CPT. CPT it's like a way of getting these model theoretic preparation theorems. And they do these theorems for all p-adic places at once when they try to get some motivic integration for all p-adic places. So it seems quite plausible that you should do something like this, but I'm simply not sure what the right statement is.
Do you think there could be a condition like some p-adic condition so that ln implies n?
Say again?
Could there be a p-adic condition which, when satisfied, and then you were log-Noetherian, you'll automatically be Noetherian?
That would be great. I mean, it's what it feels like from this example, but I'm not, it's above my pay grade, this kind of theorem. Yeah.
Maybe you said, and it went over my head, the CJs themselves in this last part, they're also effectively.
Yeah, so once you bounded this K, then you have like an equation like this, and it's all between polynomials of bounded degree, and then you can get effective bounds by Grobner basis on everything. You can really kind of even compute the coefficients.
Because you need to compute CJ effectively.
Yeah, you need to know really the coefficients of CJ.
Essentially, the coefficients are integer.
I mean, you should reduce basically to integer coefficient. They kind of introduce extra variables for all the coefficients. But in fact, if you started with a chain that's over the integers, then really everything here is defined over Z in the first place. So you can really kind of just get this from direct Grobner basis computation. And this is why the bound is very bad. I mean, whenever you do Grobner, then you get quite bad bounds.
Questions? Okay, thank you. Thanks.